the plot that you can see at the bottom of the slide is an example of, if I remember correctly, that's PM10, particulate matter 10. All right, so that idea of non-standard data can also be used in the big data. Non-standard data can be used in the big data context. So imagine that you have a data set that is complex and too large to either analyze or store in your computer. You want to use symbolic data points to summarize the information that is contained in these data sets. So here, mathematically, how we define a symbolic data point or a symbolic random variable, I will call them S. And basically what happens is that I apply an aggregation function pi to my data, which will be the x1 up to xn, matching and mapping the set curly x to the n to a space curly s, which will be the space in which my symbol is going to live in. So of course, what we want to do is to retain the maximum relevant information from the data set such that we can perform an analysis. What we want is to get rid of all the superfluous information that is not going to bring much to the analysis. So by the fact that we're aggregating the data into these summaries, there will be an internal structure inside that summary, and also a structure, a dependent structure between the summaries. So we have to take into account these two types of dependence. So hopefully the deal is that we want to go from a big data set and collapse it into a smaller symbolic data set and be able to perform an analysis that will be as accurate, but also much faster. It would be good, and there are possibilities to use these methods for data privacy, where you can aggregate individuals into some summary, and so you can't identify individuals. So the main challenge in this field is to know how you can perform a statistical analysis for this kind of data. And we want to keep in mind that the interest is to gain information on the data level rather than the symbol level. Okay, so in 2018 with Jaslyn Lin and Scott Sisson, we proposed a likelihood-based approach for this kind of data. So the approach is relatively simple. We define a likelihood for the symbols, the L of S given theta and psi, as being proportional to an integral of G of S given X times L of X given theta, and I integrate with respect to X. So what we have there is that L of X given theta is your standard classical likelihood. So that's the model that you would like to fit. And the parameter of interest is theta. The G of S given X is basically giving you the probability that you obtain a symbol given some classical data. So what the integral does is that I'm integrating the likelihood that is in some sense weighted, and I integrate it for all the possible data sets that are going to result in the symbol that I observe. So imagine that the symbol is a histogram. You will integrate over all the possible data sets of size n that are going to give you the symbol S. And that way you're going to get the symbolic likelihood, the L of S given theta, and you can maximize it to get an estimate of theta, the parameter of the model of interest. So there are some sanity checks that we can do. You can see that if I take my symbol SI, so one of them, and I can make it collapse, so reduce the internal structure into being the single point itself, then my function G of SI given X is just simply a Dirac function, making sure that X is at Xi. And so in this way, collapsing my symbol into points, I can see that I can reduce my symbolic likelihood into the classical likelihood. So there is always some checks that we can do in the models that we develop to check that we can recover the classical result that we would obtain usually. So let's take the example of random histograms. So we have some data, x1 up to xn. They live in RD, and we have a model that we want to fit that is given by g of x given theta. We're going to assume here that we have fixed bins, so b1 up to bb. So we have, in fact, b1 times etc. up to bd bins in this histogram, because it's going to be d-dimensional. So we're going to apply the aggregation function pi, which here goes from the space rd times n to the curly s, which corresponds to counts. So it's from 0 to big N, the number of observations that I have, and it's raised to the power the number of bins that I have in my symbol, or in my histogram. And so what I do is that for each bin, I'm going to count the number of points that fell into that bin. So that's the aggregation function. The function g of s given x, so the probability that we observe the symbol given the data x, is simply a Dirac, where I will take value 1 when we have SB from observations that fell in the bin B. So we need to make sure that we match the right number of observations in each of the bins. And so if we do that, we get our symbolic likelihood that is going to be proportional to the product from B1 to B. So that's over each of the bins. And I have an integrate over BB, which is the location of the B of bin. And I integrate the model that I'm interested in, so the density of the model. All this is raised to the power of the number of counts. So what you can see is that in that case here, we have a vector of counts as the symbol, and it's going to be modeled as a multinomial distribution where the probabilities are calculated using the model that we're interested in. So this is a generalization of the McLachlan and Jones 1998 results. Okay, so if we keep going, let's do the sanity check. And what we can see is that if I increase the number of bins in my histogram, I will reduce the width of my bins to the point where they're going to reduce to single points. So if we reduce it to single points, some of them will have count 0 and others will have a count 1. And that way you can see that the integral will just become the density itself. And so we end up with the classical likelihood, and we can just recover the regular estimates. So there is some consistency by doing this procedure, because if we use a sufficiently large number of histogram bins, then we can see that we're going to recover the estimates of the parameter that we would get using the full data set. So there are approximations that are done by considering the symbolic likelihood. And so there is that level of the discretization that is based on the number of bins. What is the optimal number of bins, for example? These are questions that we still need to work on. In the case where you want to work with data that is not ID but exchangeable, we looked into this in a paper with Xin Zheng, but I won't talk about this today. So just as an example, if we want to fit the GEV distribution, so we have x1 up to xn that are GEV distributed with location mu, a scale sigma, and a shape psi. I then create a histogram with big B bins. So we have univariate histograms. I have my log likelihood function for the symbol, that is the sum over the bins. I have the counts times the log of the difference of the CDF of the GEV evaluated at the upper minus the CDF at the lower value of the bins. And so when we do this, you can see the plot on the left-hand side. So I had 1,000 observations and I had 11 bins. In solid black, you have the estimate that you would get from the GEV density if you're using the full data. And if you use the histogram that is represented there, then you get the estimate that is the dashed red line. So what you can see is that we can recover with only 11 bins a very good estimate of the parameters. In terms of computations, optimizing the log likelihood function is very quick because there are only very few terms. The creation of the histogram is slower, especially if you have lots of observations in, that are in the model. So we can see that we can perform a good fit here. Now, we need to compute, so that's one of the limitations. We need to compute the integral of the model to know the probability according to the model to fall in some bin. So in one dimension, it's relatively easy. We just need to take the difference of my two univariate CDF at the upper and lower value of the bins. In 2 dimensions, if I want to look at a square or rectangle, I now have to use 4 two-dimensional CDFs. So you can see that now if I want a d-dimensional histogram, I will need to compute for the probability to fall in a bin 2 to the d components. And so it was going to be very computationally intensive and not very viable for large dimensions. So if we are focusing just on histograms, we have some limitations. So as I said, there is the number of components needed to evaluate the probability to fall in a bin, but also as the dimension is increasing, then we will have lots of bins, and that means that the computation is going to increase also because the number of bins is increasing very fast. So that means that we're limited to low dimensional symbols or histograms. So in the SDA literature, usually you can see results in 1 or 2 dimensions, but it doesn't go much higher than that. So in principle, we could use higher dimensional information, and that's what we would like to do here. So we propose to solve this problem of dimensionality to use composite likelihood. Okay, so now I'll move on to composite likelihoods. So I'll start with a motivating example on spatial extremes. So the 2 tweets that you see here are from the Bureau of Meteorology from January last year. So there was a heat wave that was in Australia and also in New South Wales. So on the right-hand side tweet, you can say that they say temperature exceeding 45 degrees for many locations throughout Western New South Wales and Central Australia this afternoon. So typically when people want to use spatial extremes, it's because they want answers to questions such as, what is the maximum value that a process, and here we take the temperature, is expected to reach over some region of interest, so that could be New South Wales or Australia, within the next 20 or 50 years. So that's the kind of question that we try to propose some solution to in the paper with Tom and Scott that got published in Stats and Computing this year. So in that paper, we are looking at modeling the Australian temperature using spatial extremes. And so we have 105 locations because we're looking at a gridded data. That's because we have a climate model. So the data are actually simulated according to a climate model, and we have this kind of resolution. So we have 105 locations through space, and you have different records over time. So here we would like to fit a max stable model to understand the dependent structure between extreme temperatures. So what can we do here? Can we use a 105-dimensional histogram and then fit and estimate the parameters from there? So as we said before, we are very much limited to lower dimensional histograms. So what we suggest is that it may be a good idea to use lower dimensional histograms, such as 2-dimensional. So here in the plot, what you can see is that I have the information between 2 locations in space and a different level of discretization. So it can be either very rough or so precise that you have basically your classical data. So what we are wondering is that maybe we can use 2-dimensional histograms between pairs of locations which means that we will have 105 by 104 over 2 bivariate histograms. And we would like to use this to fit the maximal model. So to do that, we're going to use composite likelihoods. So just to recall how composite likelihood work. So in the standard case, you have your likelihood L of x given theta, where x is d-dimensional. So think that xi is going to represent your ith spatial location. So if we take the case where d is equal to 2, so I'm just looking at the pairwise composite likelihood, then the composite likelihood is in fact taking the product over the pairwise likelihood between xi and xj, and I'm taking all the bivariate marginal events. So I take the product over all possible pairs. So this actually works fine because if we look at the log likelihood here, the log of the pairwise likelihood is going to be an unbiased estimating equation for theta. And so if we take the sum of this unbiased estimating equation, it will still be an unbiased estimating equation for theta. And so it works well for this kind of spatial problems. You can do and define exactly the same for a higher dimensional composite likelihood like the J-wise composite likelihood. Now, what do we know about the behavior of the composite maximum likelihood estimator? Well, it's asymptotically as n goes to infinity consistent and normally distributed, where the mean is 0, meaning that we have an unbiased estimator. And the variance is given by taking the inverse of the Godambe information matrix. So that's the sandwich information matrix, where the bread is the H function, which represents the sensitivity, and J is basically the cheese in your sandwich. So you have the variability matrix. So if J is equal to D, meaning that you are just taking your full likelihood, then H and J are equal, and then you recover from the Godambe information matrix, you recover the Fisher information matrix. So really the question that we're asking here is, can we use this kind of construction to help us work with, or instead of a 105 dimensional histogram? So the answer is yes. That's why I'm giving this presentation today. So what we can do, we can define it exactly in the same way. So the pairwise composite likelihood for my symbol S is in fact taking the product of all the pairwise marginal histograms, and then I will have the likelihood for these pairwise marginal histograms, ij for dimensions ij or location I and j. So how do you work out the pairwise marginal likelihood? Well, you just take the product over the bins that you have in this bivariate histogram and the product of the bin probabilities, which is the integral of the pairwise max table distribution that you have over this bin, and you raise it to the pair counts that you have. Okay, so what can we say about the symbolic likelihood estimator if I have only one histogram? So I'm not looking here at a composite version. But what I can say about the symbolic likelihood in this case is that the estimator is going to be asymptotically consistent and normally distributed. It's going to be unbiased, and the variance is going to be the inverse of the Fisher information matrix. But you need to see that when I say asymptotically here, I mean that I need to have n to go to infinity, which is what I also said for the classical case. But I also need, and that's relatively strong, the number of bins to go to infinity, which means that the volume of the bin is going to 0. So it's very strong here because what I'm saying is I have the property of being asymptotically consistent and normally distributed if the number of observation increases, but also if my symbol is going towards the observations themselves. So an interesting question is if I fix the bins and I don't make them, I don't increase the number of bins. I'm only looking at the asymptotic level where n is going to infinity. What can we say about the properties of the estimator? So this is currently a work that is ongoing, sorry, and it's part of Prosha's PhD studies. So in the case of the composite likelihood for the symbols, it's going to work exactly the same way. So we're going to be able to say that the estimator is consistent and normally distributed, so unbiased, and the variance covariance matrix is the inverse of the Godambi information matrix. But again, we need to have this kind of double asymptotic where n is going to infinity and also the number of bins. So this is also fixing the number of bins for this case is also work under progress. Okay, but so I can give you some kind of result that we have for a simulated example. So here we're looking at the pairwise composite likelihood estimates. I have 1,000 observations simulated at 15 locations in space. And for each of these 15 locations, I will construct a single pairwise histogram for each of the pairs of locations. So the true model that we simulated from is the Gaussian max-tuple model, or it's also called the Smith model. The true values of the three parameters here are 300, 150, and 200. That's the parameters that you have in the dependent structure. As you can see in the table is that as I increase the number of bins, so as they get large, so I go from 2 to 25, then the mean and the standard error of my estimates are actually converging towards the value that I would get in the classical case. Also keep in mind
for clarity, I have to ask something. So I thought that you did the analysis letting both the number of observations and the bins grow.
Yeah.
At which rate do the bins grow as the number of observations? Do you let them grow linearly? Or do
so here in this example, the number of observations is fixed to 1,000.
But the results you had on the previous page, I thought that it was an asymptotics in both n and the bins.
Yes, that's right.
So are they like treated separately, or do you let the bins grow as the, I don't know, square root of the number of observations?
No, we do it separately in that case.
Okay.
Yeah, thanks, Matthias. And in this case here, so it's fixed, and you see that even if you fix n, we're going to recover the classical estimates. So in the case, Matthias, that doesn't mean that we can show unbiasedness or anything like this. But we still go towards the classical estimate that we know are going to be unbiased.
But so just a final question there. So if you fix n, can you really let the number of bins go to infinity? Because you cannot have more bins than you have observations, I guess.
Yes, you can. You'll just have many bins that will have zero counts in them.
Okay, thanks.
So you can just, if you, in that case here, actually, if you increase the number of bins to infinity, you'll just have, you'll just recover your points exactly. And then in the likelihood, what you have is you have these integrals that just become the density itself, but they are raised to the power 0 or 1. So wherever you didn't have any observation, then they will just disappear. Yeah, so in that table here, what you can see is that as if you take, for example, just 10 bins, it seems like we have acceptable results compared to what you would get in the classical case. So what is nice here is that we show that we can provide results that are very close to the classical result for a moderate number of bins. But also the most important case, and the reason why we do this, is in terms of computation time. And so here we have another example where I have 25 bins, and I'm going to compare the case where I have 10 locations, so same as in the previous slide, but also 100 locations, which is more what you have in applications, and that was what we had, or roughly the number of locations that we have in our application for the Austrian temperatures. So what you can see on the left part of the table is that when we have n, so I make n go towards infinity, or it goes large, sorry. The time to compute, so TC is the time to compute for the classical case, the time to maximize the likelihood. So if we have 1,000 observations, it takes 71 seconds, but you can see that if you have a large number of observations, you get to 31,000. TS is the time that it takes you for the optimization of the symbolic likelihood. And that one stays relatively constant around 22, 24 seconds. It's because the number of bins is not changing here. So as I'm not changing the number of bins, the difficulty is always the same. I just have already aggregated my data. One thing to keep in mind is that we can have time that comes from the aggregation into histogram. So we use two different methods. The first one is, so you could use R, so that's the fourth column. You can see that in R, it will start to take quite a lot of time if you have many observations. But a way to bypass that is to use the computing resources delta rho, which make it a lot faster. So for 10 locations, you can manage it, it's okay, but you can still see that we have already big gains in time. But now if you have 100 locations, what you see is that now I was not able, or probably not patient enough to compute for 100 locations and 1,000 points using the classical case. However, I can do it for any of the number of observations that I specified here using the symbols, and it takes less than an hour to do it. So usually in the literature, people stop around 20 locations because it gets computationally too intensive if you just do the usual composite likelihood for max-level models. So here we can show that using the symbolic approach is very efficient in terms of computation time. All right, so I will refer to you to check the paper if you're interested in this. We have many more simulations and some cool results there. Also, the more detail about the real data analysis. So we talk about including the effect of number of histograms in the simulation. Also the allocation of the micro data, so the underlying data into the different histograms. And also we compare the symbolic pairwise composite likelihood and the triple-wise one. Now I'll focus on a second problem for high-dimensional histograms is the logistic regression. Okay, so again, some motivating example. We got some data from colleagues at QUT that is represented here. So it's satellite data. We have about 250,000 pixels in Queensland, and they're going to represent different crop types. We have 7 response categories, so from bare soil, that is in black, to wheat, that is in yellow, with some known ground truth. And in that case, it's going to be a little bit confusing, but we also have 7 explanatory variables in this model. So what we want to do is a multinomial logistic regression. So you could do it, but in that case, it will take a bit over 8 hours to do it. So a question that we ask ourselves is, can we use symbolic data analysis to kind of keep the same level of prediction accuracy, but also speed things up? So if we look at regression models, you have xi, yi, your pairs, where yi is the response lives in the space omega that is composed of big K outcomes, and then x are your predictors, and they live in RD. So what you want to do is predict the category of yi given the vector xi. So just for the purpose of the talk, I'll focus on one versus rest logistic regression, where the odds ratio are log linear. So that means that the probability that the outcome is k given x over the probability that y, the outcome of y is not k given x is log linear. And so the standard classical likelihood for the 1V rest logistic regression is the product over I1 to n, so the number of observations that you have. And you have the probability that the outcome of the outcome yi takes value yi given xi, but also you need to take the product and all the products, saying that the outcome is not going to be yi, it's different from yi. So you have all these remaining products in there. Okay, so what we would like to do is construct a 7-dimensional predictor histogram. So because my predictors are 7-dimensional, what I want to do is for each of my outcomes, construct a 7-dimensional histogram. So I can do this and applying the standard symbolic likelihood that I defined at the beginning of the talk. You can write a histogram-based likelihood for my bold S, which is composed of 7 histograms that are also 7-dimensional. So 7 histograms because I have 7 outcomes, and 7-dimensional because I have 7 predictors. Sorry if that's a bit confusing. So what you can see is that the likelihood then is the product for each of my outcomes. So my k outcomes, let's say, and then I'll have the product over the bins that I have in each of these 7-dimensional histograms. And there I need to do the integral of each of my probabilities, and everything is going to be raised to the power. So one issue is that the integrals here, you can only do it analytically if you have one predictor. More than one predictor, you will need to do use some computational tools for that. So before I go any further on this, I just want to give you some interesting result that we have on the existence of the MLEs. So in the standard case for the logistic regression, you know that beta hat, the maximizer of your likelihood, exists and is unique if you have, if you don't have, complete or quasi-complete separation of the data. So that's the result from Albert and Anderson from 1984. Basically, the separation of the data is that if you had a binary outcome, so 0, 1 for your y, you have separation if all the values y is equal to 0 is going to give you specific value for your predictor x, for example. So if for all y0, x is less than a value 5, and for all y equal 1, x is greater than 5, then you have separation. And so using a slightly different and modified version of separation for histograms, we can say that the maximum likelihood estimate using the symbolic likelihood exists and is unique if there is no complete or quasi-complete separation in terms of histogram. So obviously 0.2 is stronger than 1. That means that 2 is going to imply 1. And so there are some interesting things happening here, because if there is no existence of my symbolic estimator, maximum likelihood estimator, that means that there is no existence of the classical one. And then you can do the reverse. If the classical one exists, then it means the symbolic one exists. But there are some cases where you can say, well, the symbolic one exists, but it does not imply that the classical one exists. And so there might be some possibilities where we could use the symbolic version, so SDA, when you can't actually use the classical data. It gets a little bit crazy if you think of the sanity check that I was talking about, where you take the symbol to kind of converge to the data, the underlying data, because then that means that existence of the MLE at the symbol level implies that there is none. So it gets maybe a little bit tricky, but I think it's definitely worth investigating. So going back to the original problem, so we have to look at these integrals that we need to compute. So the only thing that we can remember, or that we should remember, sorry, is that they are very easily computed if we have only one predictor. So seeing this, the thing that we thought about is, okay, if we can do it relatively easily when we have one predictor, maybe we can just abuse the idea of the symbolic composite likelihood and use one-dimensional histograms for each of my predictors, right? So using this idea, we say, okay, we're going to construct composite likelihood version using all the univariate predictor likelihoods. You could also do it with two-dimensional or higher, but it's going to be more difficult because you will have to compute and do these integrals. So the good thing here is that we get around the high dimensional integration. In one dimension, it's very easy to do. The bad thing is that each of the marginal events are not unbiased estimations. And so that means that we're not going to have a true composite likelihood function. It's an approximate composite likelihood function. And so we also know that it's well-known result that the estimates that we get for the parameters are going to shrink towards 0. So there are some possibilities to go, there's a partial fix. So after the good, the bad, we have the ugly, the partial fix. So using the result from Kramer, you can do some adjustment to reduce the bias. So you're going to reduce the bias, but you're not going to eliminate it. However, you can think that in a prediction context, this is okay as soon, so the reduction and the shrinkage of the parameter value towards 0 is okay, as soon as what you're interested in is the prediction, not the value of the parameters, if basically the magnitude and the differences between the parameter stays consistent. At least that's what we found in practice. So we're going back to our example here. So we have our 250,000 pixels, we have 7 response, and we're going to use the one-dimensional predictor that are going to be aggregated into univariate histograms. And we're going to include a lasso regularization in the model. So just a few plots, representations. So these are for 6 of the predictors. And you have the histograms the univariate histograms for each of the different crop types. So you can see already that the one-dimensional predictors can identify some type of crops. So the light blue one, for example, is bare soil, and you can see on the left-hand side, the second plot, or at the bottom right, that you can already identify it using these predictors. So it gives us some hope. And so some of the results, we're looking here in the table at prediction accuracies for each of the crop type, but also the overall prediction accuracy. So we have the columns, and we have the number of bins in the univariate histograms going from 6 to 20. And the last column in blue is the prediction accuracy that you would get if you were just using the raw data itself. So what you can see again is that you would get some relatively good result if you use only 10 bins. So the prediction accuracy, the overall one is 76.4%, when it's 78.1% if you're using the raw data. One thing that is important to note is that the poor performance seems to happen when we're looking, for example, at wheat. So we have prediction accuracy of 4.8 instead of 10.3, but that's in the case where we have relatively low number of data points that are aggregated. Also, and the major thing here is that the computation time, so the last row in the table, if you use 10 bins, it takes 221 seconds, whereas if you're using the classical data, it will take about a bit less than 2 hours to do it. Okay, so again, in this paper that is available online, we have done more simulations, and there is also an application to a supersymmetric data set. This data set, we got it from another paper, a JASA paper from Wang in 2018, where the author is looking at subsampling method to increase the computation time of logistic regression. So I'm not presenting anything about this here, but we did a comparison, and we can show that we reach the same prediction accuracy level as in that paper, but we are much faster than this subsampling method. That's just one of them, so it does not necessarily mean that it's going to be the case consistently for all methods. So. Okay, so just a little bit of discussion to wrap up. So we've used some symbolic composite likelihood. It's just a natural extension of the symbolic likelihood, same kind of extension as what you see in the classical case from the regular likelihood to the composite likelihood. It has the advantage to avoid these big integrals that are required when you want to use high-dimensional histograms. And it seems to be useful for the logistic regression, even though the composite is not really suited in that case. So there's some open questions other than the ones that I've already stated throughout the talk. Is maybe there are some better ways to actually deal with the high-dimensional histograms and the integration. Maybe there are better ways of compute these integrals rather than going through composite likelihood methods. Also, how can we really do high-dimensional regression for symbolic likelihood if we don't want to go by symbolic methods? And also, there are many other open questions. The design of the symbol is a recurring one. And we're looking into, at the moment, or Proscia is looking into the properties of the estimators. So that's it for me. Thank you for listening. Here I've listed the three papers that I mentioned mostly in the talk. And if you need to contact me if you have any questions, here is my email address. Thank you.
Thank you so much, Boris. So we open the floor for questions now. So if you either speak up or raise the hand, and I'll let you speak. I don't see any hands raised on the chat. No questions on the chat either. So I think I can ask one in the meantime, Boris. So when you were looking at the bivariate, so you had this multivariate spatial data.
Yep.
And in order to make that tractable, that composite likely tractable, you were looking at the pairwise histograms, right?
Yeah, that's right.
Yeah. So does that correspond to, like, if you think about, like, what are you actually doing with the spatial correlation there? Or are you like only keeping the correlation between one of the cells and its neighbors when you do such an approach, or?
Yeah, so this is like, so composite likelihood, it was for spatial extremes. It was introduced in 2010 in a JASA paper. Scott was involved in this actually. So what happens is that you're doing this kind of approximation of the likelihood by using the pairs. But because you use the pairwise density, and usually you also have, like a para-exponential correlation function. So it just depends on the distance between two locations. So in that way, in each of the component that you're taking, the pairwise component, then the correlation, the spatial correlation is taken into account.
Okay.
So in the case that we do here, it's very much the same. We just apply the same idea. So we're not losing anything about the spatial correlation.
Okay. Christian, you have a question?
It's in the chat if you want to read that out.
Oh, I didn't see that one. Yeah, Boris, do you have a look at the chat?
Yeah, sorry, I'm trying to put it. Where is the chat? Sorry, I don't use Zoom very often. Yeah, chat. Okay, I've got it. So bins in the PIM mapping, always measurement will be quantized. as the bin in the PI mapping goes to infinity, it seems to turning continuous raw data into zero inflated quantized data. So what do you mean, sorry, Christian, by quantized data?
So instead of having, let's say, 50 counts of a continuous number, you've now bin them by the bin range. So they'll become, if you had a bins of 0.1, you'll be kind of rounding off to 0.1, much like you would on a machine. And you'll have a lot of noughts because you'll have a 0 for each time you don't observe that one. So it's inflating the amount of counts you have when n is large and putting them in as noughts. If we just throw away the noughts and we quantize by the bins, this seems like a nice way to deal with quantized standard counts instead of bins. Would that be fair to say?
Yes, sorry, I'm trying to fully understand, but I think so. There are many ways to actually define the histogram. You can, you know, at the moment it's fixed bins, but they don't have to be fixed, for example. You can make them move, they can have variable width. Instead of having random counts, you can have the random bins and fixed counts, different things like this. Does that answer a little bit your question?
I think so.
Okay, so next question is from Robert.
Boris, nice presentation.
Thanks.
Now, with the with the composite likelihood, do things get better if you so you've got pairwise stuff conditional on the rest or something? Do things get better if you have more on the left-hand side? If you've got 2, 3, 4 things on the left-hand side, condition on less things on the right-hand side, you know, the product of these?
What condition?
Oh, well, in the composite likelihood, you've got a set of conditional distributions, right?
No, they're just the pairwise distributions.
Yeah, just the pairwise. Well, is it going to be better if you have triples, etc., instead of 4 at a time instead of 2 at a time?
So that's something that we looked at in the spatial extremes thing, and that's what I was saying in the paper. We looked at, rather than using the pairwise, using the triple wise, and so you can look at relative efficiencies for your estimates.
And what happens there? I can't remember.
So I didn't talk about it. I just say, okay, go and look in the paper. But yeah, you're going to improve it. You're going to improve the relative efficiency of your estimates. If you...
So basically, the higher the dimension that you can tolerate, so you can't tolerate the whole thing. That could be like 10 or 20 or whatever.
Yeah.
But if you can do higher dimensions than 2, like 3, 4, 10 or whatever, then you're going to be, you're likely to perform better.
Yeah, that's right.
Okay, so that's interesting. By the way, relevant is with a VANT, isn't it? So now the question is, do we have any analytic proofs for what sort of theory do we have about the composite likelihood doing well as we scale up the number, the number of components become less by using more variables in each one? Do we have any theory for that?
There is nothing. So in the spatial extremes literature, there are a few papers that looked at comparing for different models using pairwise, triplewise methods. Actually, recently this year, I published a paper with some co-authors where we looked at going to higher levels. So for example, 10-wise composite likelihood, you can see that the relative efficiency is going to increase. There is that trade-off between an increase, maybe a small increase in the relative efficiency, and a gain in computation time. So there's that trade-off, but there is nothing theoretical that has been developed on that.
Yeah. Okay. Okay. I've got another question, but that can wait until your 2:00 seminar. Now, I've got another question, but maybe somebody else wants to ask a question.
Is there any other question? Otherwise, I'm happy to let Robert ask his second question.
Any other questions?
Yeah, I want to hear yours, Robert. Go for it.
Yeah. So, okay, now I've forgotten it, but it's terrible. So, can we? So the composite likelihood is one way, but clearly, putting variables that are correlated together into sort of bigger groups might be something that will work well in the composite likelihood. So rather than just and still cut down on time. So variables that if there's 4 variables that we think are highly correlated, and we can look at them in some sense or whatever, or parameters or whatever, then we might put them together rather than sort of just say we've got 100 variables and then we take all combinations of them to do the composite likelihood. So be a bit more selective, be a bit faster, but take into account the more high dimensional stuff, the dependence in more high dimensional stuff.
Yeah, for sure. There are probably better ways than taking, because taking absolutely all the pairs is maybe not really useful. When you think in these spatial cases where by taking all the pairs, that means that I'm taking pairs of locations that are very close to each other, but also the ones that are like very far from each other. So there is maybe more, a way to like put groups together, for example, as you say, like the ones that are close correlated, then you put them together.
I'll put a question in the chat about that. Suggestion would be to use a wavelet decomp to do that. So you'd group together the large scale ones at that top level, and that gets you large scale changes in weather. And at the small scale ones, you pick up the local effects. And again, like was just said, you're expecting it to be spatially and temporally sparse. So you can band that structure in a nice way.
That's interesting. Yeah, that's a good suggestion, actually. I didn't know about it, but yeah, that's something that is worth trying, I guess.
Okay, any more questions for Boris? So if not, we close the seminar. Thank you so much, Boris.
Well, thanks, everyone.
Yeah,
thanks, Christian.
you're getting a lot of virtual claps. I'm pretty sure about that. It was an excellent talk. Thank you so much. And Boris, I recorded it, but I think I missed like the first 2 minutes or something, 2 or 3 minutes. But that's all right. I'll send it to you, okay?
Yeah. There was nothing important.
Yeah, with the elephant slide in the first one. I like that slide.
Yeah, it's okay. It comes back, all right?
So send us the send us the elephant slide.
So that one. Did you see that one, Robert?
Oh yeah, I'm looking at it now. I'm looking at it now.
Do you know where it